All right, so you ready? This is what we're going to study. Section 11.2 is a piece of string, okay? It's going to be pretty interesting. Think so? Piece of string. Let me label a couple points here. Call it A and say B. Later on, maybe I'll give those some more specific names. But for right now, we'll call it A and B. And well, let's have a little fun with this. Let's take this and trace it around like that. A little bit farther, and then do the same thing on the top side of this. Hey, that came out pretty good. So, in your mind, what does this shape look like? Circle?
Oval maybe?
Yeah, oval. Now, in this section, it's going to have a specialized name. It's called an ellipse. All right, there's no C in here. It's not an eclipse. It's not what we saw back on April 8th. It's an ellipse. Now, ellipse has a lot of special properties, but one thing I want you to notice about the ellipse is kind of what happened when I traced it out. The length of this string didn't change at all, did it? The length of that string was constant no matter if I was here or wherever. It was still the same length of string. So that's one of the defining properties of an ellipse, is that this distance, call it D1, this distance D2, to this point, say, D1 and D2, the sum of those are always going to add up to the same thing. Now, that's not something you're going to have to worry about, but what you are going to have to worry about is finding these points. These points that help define our ellipse are called the foci, F1 and F2. So they're pretty cool points. We're going to find some points like that. Now, those points help create properties of an ellipse. And let's just look at a few properties of ellipse, places you'll see an ellipse. One of them is in the shape of orbits. And a lot of functions, or a lot of things have orbits that are in the shape of an ellipse. Now here's a more detailed presentation of what I just did here. But let's take a look at where else you'll see an ellipse. In Washington, D.C., in front of the White House, there's an ellipse. A lot of protests and a lot of marches go on around there, ceremonies, etc. The Earth orbits the sun in an elliptical shape. Now the sun is at one of those special points, the foci of an ellipse. Ironically, we're actually farther away from the sun now than we will be in January. So, wow. Now the reason for the seasons is not how far or how close we are to the sun, it's how we're tilted towards the sun. So right now in the southern hemisphere, they're experiencing winter, whereas we're experiencing summer because we're tilted towards the sun. In fact, I think we're getting a heavy dose of summer today, aren't we? Yeah, unfortunately.
Thank God.
So this is a lithotripter. This is one of the really cool uses of the shape of an ellipse. Hopefully you'll never actually have to use one or see one in person. But what they do is they've got an elliptical shaped reflector down here in blue, and they put an electrode right at one focus of an ellipse, and it directs energy to the other focus of an ellipse, which is up here in green. Hopefully that's where you position either a kidney stone or a gallstone so that it can be crushed by some energy waves and you can pass it through without having to have surgery. I've heard they even put these things on trucks and drive them to your house. There's acoustical properties of an ellipse. There's a certain someone special to me about a bunch of years ago, and you can whisper in one end of the room. There's the Whisper 5 Science Center, and way down here at the other end, about 120 feet away, somebody else can hear you there. It's just amazing.
Oh, it's like, I forget what museum in New York it is, where you can stand on the opposite side of the atrium.
Oh, I know what you're talking about. I saw a video on that.
So, and then last but not least, we're going to be traveling to the moon. Those kind of orbits, when you travel, are elliptical shape, and there's special things you have to do to, maintain your orbit and get to the right spot. But anyways, there's kind of a brief introduction into ellipses. Let's take a look at what's going to be for us, and that would be with our handout here. And we've got a nice equation of ellipse here. One of the characteristic equations of an ellipse is that both of these terms, you're going to have two squared terms, an x squared term and a y squared term. and you're gonna be adding those two things together. Now, if there was a subtraction there, it'd be a lot different, but it's gonna be an addition. Not knowing much about ellipses, at least from this class and our experience here, what you could do is you could say, you know what, let's find some x and y intercepts. That is, let's set x equal to 0 or set y equal to 0 and solve. So for instance, if I set x equal to 0, what would happen? Well, I get y squared over 4 equals 1, because the x squared term is gone. How would you solve here? Yeah, multiply both sides by 4, and I hope you don't pull out the quadratic formula. Rather, what would you do? What's the quick way to solve this one?
Square root.
Square root property. Don't forget the plus or minus. So x is plus or minus 2. So you got 0, 2, and 0, negative 2. We can play the same game for the y's. If you set y equals 0, you're going to find the x-intercepts. That's going to give you x squared over 16 equals 1. And I think you can kind of guess what's going to happen. X squared equals 16. What does x equal? Plus or minus 4. So there's going to be 0 for y, 4 for x, and negative 4 for x. So two solutions. Make sure you do both of those. Now, those two solutions are already graphed for you, and we played kind of fill in dots or connect the dots in between. We've got our y-intercepts at 0 and 2, 0 and negative 2, and you got your x-intercepts here. And the rest of it, you're gonna have to kind of sketch in freehand when you do these on your own. Now, of course, on this one, I've already got it sketched in for you, and that's fine. One of the things that we're gonna need to always find is the vertices of the ellipse, and that's what these points are right here. Those are the vertices. It's just moving up and down from center. In fact, there's a quick way to do this that doesn't involve all of this. And this is really what I want you to see from this example. I'm going to rewrite this equation as x squared over 4 squared plus y squared over 2 squared equals 1. That's how I suggest you graph all your ellipses, is put it in this form. Now, there's going to be another example of like this a little bit later, where putting in this form is really the big key, and it's something you could expect on a test, say maybe Wednesday. If I put it in this form, then let's look back. I had x-intercepts at 4, 0 and negative 4, 0. That distance, that 4, corresponds to this distance right here. That's a distance of 4. So, all right, 4 and 4. And then in the y direction, I have a distance of 2. So these denominators tell me how far I have to move from center to get my vertices. And that's a good thing. It's kind of nice when you have that. You're in good shape. You can graph these pretty quick. Now, there's one other major thing that I need to tell you, and that is, how are you going to find the foci? Focus is singular, foci is plural. So in general, when we're dealing with the equation of ellipse, it's going to be x squared over a squared plus y squared over b squared equals 1. To find the foci, there's going to be, well, you're going to have to move a distance of c away from the center, where c squared is defined as a squared minus b squared, or b squared minus a squared, whichever one is positive. Now, depending on which one is positive, subtract it, take the square root, and then you can find c. So in our case, that's going to be c squared equals 4 squared minus 2 squared. So let me solve that over here maybe. C squared equals 4 squared minus 2 squared. 16 minus 4 is 12. So C is going to be plus or minus the square root of 12. Square root of 12 is something maybe you want to get off your calculator. I think it's going to be about 3.4 something. 3.464? I don't know, let's find out.
It's 3.4641.01615.
All right. It's about 3.464. Okay, great. So 3.464. Now I don't need all that accuracy. It's just going to be someplace out here. It's going to be at square root of 12 and 0 and negative square root of 12 and 0. Those are where the foci are for my ellipse. Great. Now the foci are always going to lie along the major axis. This is the minor axis. What do you think is going to distinguish the major axis from the minor axis? A little bit more than that. How about I tell that this is the major axis and this is the minor axis? Yeah, it's the length. The major one's just going to be the longer one. Yeah, Adam?
I had a question, so is A and B, are those just like 16 and 4?
Yeah, they're going to be these denominators. So now I could have written this problem as x squared over 4 squared plus y squared over 16 squared, and then would have been taller than it is wide. And in that case, the foci would be along the y-axis. They'd be up and down rather than left and right. Because the major axis is where you're going to find your foci, and the major axis is always the longer one.
So would you always write A as a bigger one?
You can. You know, I just always do it one of two ways. Either I subtract them and take the absolute value, or I just subtract the smaller one from the larger one so that it's always positive. So it doesn't really matter, you know, as long as when you take the square root, you're taking the square root of a positive number. Amy?
Would you not want us to split it up? Because technically you can take out a 4.
Yeah, you could write that as 2 square roots of 3. Yeah. So this is 2 square roots of 3, but that's not something I'm really worried about. You're going to have enough to worry about on this exam.
Okay.
So, I mean, it's great. You should be able to do that, but you're not going to lose any points if you didn't.
Okay.
All right. Appreciate the question. So let's take kind of a quick look at Desmos link on this one. Oh, some other places you'll see the shape of an ellipse, elliptical orbits. So I don't know if you guys really remember it or were paying attention at the time, but a few years ago, Pluto got demoted. It's no longer considered a planet. And I know, kind of like, boo. I mean, space is pretty lonely. We need all the friends we can get. But part of the reason for that is because its orbit is tilted compared to everybody else. I mean, take a look at this. It's tilted at like, I don't know, 20 or 30 degree plane from the rest of us. So that's part of it. There's other reasons for that as well.
It's not like something that.
Well, it's technically is probably a member of the Kuiper Belt if you wanted to be very, very specific about it. Let me see if I can't go back up here and open up this. There we go. So there's our first one. Going back to your question, Adam, if I interchange these, if I make that a 4 and this is 16, then all of a sudden it's taller than it is wide. So the major axis is now going to be along the y-axis, and instead of moving left and right, a distance of square root of 12, you're going to move up and down a square root of 12 to find the foci. So let's see. Yeah, there we go. All right, let's take a look at the next one then. Yes?
When we did the 4 squared, converted 16 squared to 4 squared and 4 to 2 squared, that was to make the foci.
That was to find the foci. Yeah, okay. This calculation of C is where you're going to find the foci.
And so, if it wasn't a square root, it wouldn't be an ellipse, right?
No, it could be a square root. You know, they could work out pretty nice. These could be nice numbers. If I had, say, 5 squared and 3 squared.
What I'm saying is, like, if we had 15 instead of 16, then it wouldn't be a circle, or would it still be a circle?
So the reason you get a circle, in fact, you know, I appreciate your question. Let me do it this way. Let's put in, let's say, a D here as a slider, and put in a D squared. 1, 2, 4, oops, 2, 4, like this. The reason you get a circle is if these two denominators are the same. So let me do this as 4 squared. All right, so now I got a very narrow ellipse, but as I make the value of d closer and closer to 4, what's happening to my ellipse?
It's becoming more circular.
Yeah, it's becoming more and more circular, and when I finally get, bam, right there, that's a circle. So you can kind of consider a circle as a special case of an ellipse, which is really what it is.
Oh, okay.
So if these two are equal, then yeah, I'd just be graphing this as an ellipse. In fact, maybe I can come up with a demonstration for you about that. Let's see, I don't know if I have one of those, my Desmos. Yeah, so what's going to happen is that you can deal with something called eccentricity. Here's your foci, and let me see what happens to those foci as I get this closer and closer to 6. So you're going to see something gets rounder and rounder as we do this. And what do you think is going to happen to the foci when I get to 6? Yeah, it's become the center. So that's really emphasizing that a circle is a special case of an ellipse. The two foci have met in the center, and those directions, up, down, left, and right, are the same. In fact, in any direction, you have the same radius. So, great question. All right, let's keep going. Example B here. Now, the big thing that helps us out when we graph these things is to rewrite them so that you have a denominator of a squared term and another denominator of a squared term. Now, I can do that for this one. So I have a y squared over 3 squared. But what am I going to do for the x squared?
X squared over 1.
X squared over 1, but I want it squared.
1 squared.
Yeah, 1 and 1 squared are the same thing. So in this section, all your ellipses are going to have a vertex, or excuse me, a center at 0 and 0. But what I want you to do is think for a moment. What's this graph going to look like? Which direction is going to be bigger, horizontally or vertically, along the y-axis or along the x-axis? So I'll give you a couple choices. Let's see, let's shut this one off. It's going to be something like this or something like this. First one or the second one? What do you think? First one, yeah, absolutely, all right. So what you should have on your graph is something with vertices at 1, 0, negative 1, 0, 0, 3, and 0, negative 3. Those should be your vertices. And then you just play connect the dots for all the stuff in between. Now we are going to have to figure out the foci as well. So what is it that allows us to calculate the foci?
B squared minus a, or a squared minus b squared.
Yeah, so it's going to be the bigger square minus the smaller square. So in this case, c squared is going to be 3 squared minus 1 squared, or 8. So c is going to be the square root of 8. And yeah, you could write that as 2 square roots of 2. That's fine. I'm not worried about that. Square root of 8 is about 2.4, 2.418? 2.81, yeah, 2.828. 2.828. So square root of 8 is not quite all the way to 3. So your foci are going to be here and here. Let's write our vertices. We've got 1, 0, negative 1, 0, 0, 3, and negative 0, 3. And then the exact coordinates of your foci are going to be 0 and negative square root of 8, and 0 and positive square root of 8. Okay? and that's it.
And whatever the larger, square root is, that's where the foci would fall.
Whatever the larger axis is, the longer axis, that's where your foci are gonna be. So for instance, if I try to put the foci here, if I moved a square root of 8 to the right or square root of 8 to the left, I'd be outside of my ellipse, and I wouldn't have that anymore. So it's kind of annoying. All right, and I'm afraid that's it. That's all we're doing for the graph in B. Are we good there? Yeah? All right. Now, we've kind of seen this in my demonstration just a minute ago. Let me go back to it. This is a perfect circle. And as you move farther and farther away from that, then your ellipse looks more and more cigar-shaped, and your foci are getting out near the extreme edge of your ellipse. But the ratio between these two denominators, say 6 and whatever this is, let's make a nice even one. So this is 6 squared. 6 squared. So that's 6 squared and this is 5 squared. That ratio of the smaller one to the larger one is called the eccentricity. So that's something that measures, you know, how circular shaped or how round an ellipse is. Now, part of the problem with Pluto is that it has a very eccentric orbit, so that's a little knock against it being a planet. Not that I'm campaigning for it, I have, you know, kind of partial to Pluto. On the other hand, you've got something like this, which has an eccentricity of 0.1. That's very nearly circular. In fact, something that plagued early astronomers was the fact that our eccentricity is so small that they thought we had a circular orbit instead of an elliptical orbit. So there's the eccentricity of different planets. You can check that out there. Let's calculate the eccentricity of this one. Let's see. Pardon me a second here. And trying, no, just hang on one second. Tell you what, let's move on to example E. I want to look something up real quick. Here we go. Example E. Let's work with this one, see if we can't find the vertices, the eccentricity, the focus, etc. But again, your big challenge in working with these things is the fact that your equation is not given in the nice form that we had, like say here. We put that in a nice form. So let's look at the equation for example E. If I want to write it in the form of x squared over a squared plus y squared over b squared equals 1, what am I going to do here? What do I have to do? Divide by what? Good. Divide by 50 on both sides. So we'll start with that. I'll take 2x squared plus 25y squared equals 50. And we're going to divide everything through by 50. How does that simplify? All right, so it's going to be x squared over 25 plus y squared over 2 equals 1. Thank you both. Now this first one, I can rewrite it as x squared over 5 squared. That's pretty easy. But somebody different here. What am I going to do with the second one? How can I write that as something squared? What would I square to get that? Somebody said it. Yeah, square root of 2. square root of 2. As far as finding your foci is concerned, well, let's see, let's find your vertices first. So the vertices, let's see, I'm gonna write them up here. We're gonna start out at the center. Now in section 11.2, the center is always 0, 0. That's not gonna be the case in section 11.4, where we're gonna start changing things up. But the center is at 0, 0. So if I move 5 to the left and 5 to the right, Abby, what coordinates would I have for my vertices in the x direction? Can you picture that? Let me pull up a graph maybe. So let's see, is it this one? No, it's just this one. Right there. So I need to move 5 to the left and 5 to the right. What are the coordinates of my vertices going to be there?
So you're moving the -5 over 5?
So you're starting out at 0, 0, and you move 5 to the left. What's the coordinates of this point?
0, 5, -5?
-5,
-5, 0, sorry.
-5, 0. There you go. So we got -5, 0, and what's the other one?
5, 0?
-5, 0, and 5, 0. Good. Now that's in the x direction. So we moved 5 to the left and 5 to the right. How about the y direction? Why don't you keep going, Abby? What are the coordinates going to be if I move in the y direction? So you can-
Positive square root of 2, 0. 9 would be 0,
0 and
square root of 2,
square root of 2, good.
and then 0, negative square root of 2.
Perfect. So those are going to be my vertices. Great. Thank you so much. Let's see about the foci. Adam, how am I going to find the foci here? What calculation am I going to put in for c squared?
25 minus 2.
Yeah, so it's going to be 5 squared minus square root of 2 squared. 25 minus 2 is going to be 23, so c is going to be plus or minus square root of 23. I'm not sure you really need the plus or minus there. I do it because it's out of habit. But I need to find my foci. Now, which axis is going to be larger, the longer one? In the x direction or the y direction? The x direction. So Ryan, what are my foci going to have as coordinates?
Negative root 23, 0.
Perfect.
Root 23, 0.
So negative square root of 23 and 0, and square root of 23 and 0. That's where my foci are going to be. So here's my vertices. All 4 of those. Vertices. And then my foci. So not too terribly much expected from you in working with an ellipse. But the big thing that I keep on coming back to is that you need to put it in this form in order to graph it. So let's move down to this next one, example F. I'm going to spill over onto a new sheet for example F. So let's see, 3, 4. Just not going to have quite enough room here. Example F. 9x squared plus 4y squared equals 1. And, well, this is kind of a bummer. This is not exactly in the right form that we need to graph an ellipse. So, bless you. So what am I going to do?
-1.
Is it 1 over 9 and 1 over 4? 1 over...
So what you can do is you can rewrite this. Now this is a trick. Now I would definitely know this trick. I'm strongly suggesting that you know that one. So I'll write this as 1/9, yeah.
Oh,
Nudge her again, so that she gets the message.
I got it.
this and Pluto.
All right.
Okay, I knew I was close.
So this is 1/1/9. How would you write 4y squared?
It's gonna be 1/4.
No, it's not gonna be 1/4.
Why not?
Oh, wait. Oh, yeah, you're right. Yeah, 1/4
Why?
here. Okay. All right.
Wait a
Never mind.
minute.
All right, sorry, no, I misinterpreted what you said. My bad. All right, but we're not done here.
It's an attack.
We're not done here. Kiki, what else do I gotta do? It's not quite in the same thing that I had and want. I want something x squared over a squared and y squared over b squared. How can I rewrite this so that I get that? No, because I need that 1 on the right-hand side. If I multiply by the LCD, I'd ruin everything for myself. So I'm really close. What, can you imagine squaring something to get this? What would you square to get this?
It's just gonna be 3.
Well, let's do it a piece at a time. What do you square to get 1?
It's just gonna be 1
1,
over 3 squared.
1/3 squared, and
1/4.
1/2 squared.
I was trying to say 2 before it came out.
So we could negative, like we could do 2 negative squared or -2.
No, the vertices aren't going to be at 3 and -3 and 2 and -2.
But doesn't -2, like to the power of -2, doesn't that make it like 1/4 and 1/9?
Oh, if you want to, but you want to write it in this form because you need to know what your A and B are. You want to know how far to move in which direction to find your vertices.
Gotcha.
So eventually you want to write it in this form, and I'm going to take the moment to graph these. If you guys want to borrow a ruler, I've got some up here. So let's take a look here. Which is bigger, 1/3 or 1/2?
1/2.
1/2, a little hesitation there.
I didn't say.
Yeah.
Amen, okay.
All right, so let's see, in the x direction, Johnny, what are my coordinates gonna be, please?
1/3.
1/3. And what else?
And 1/2.
Let's finish off this one first. I need an x and y coordinate.
0.
0, and let's go over here.
1/9.
No,
Oh, -1/3.
-1/3, good, and
0.
0, thank you. In the y direction, Brandon,
1/2, comma 0, and -1/2, comma 0.
almost. What do you need to fix on that? We're going in the y direction.
Oh, flip it around, so it's 0, comma 1/2.
There you go. 0, 1/2, 0, -1/2. Good. And then it's just a matter of playing connect the dots for these things in between. And I'm not going to be too careful, too picky about your graphs. The deal is, I won't be too judgmental on yours. You won't be too judgmental on mine. It looks more like a football.
I was about to say, I was.
Yeah, I know. All right. I knew you were about to give me some grief somehow. The only thing that I'm really concerned about is that when you draw these things, that you don't draw them with sharp edges. If you were to draw something like this, you know, connecting the dots like that, I'd be most unhappy. But, you know, as long as you do a reasonable attempt to make them somewhat round, that's good. Where am I going to find the foci, in which direction? Up and down or left and right?
Up and down.
Up and down. So I need c squared, and here again, it's nice to have these things in this form. C squared is just going to be the larger one, 1/2 squared minus 1/3 squared, 1/4 minus 1/9. Let's convert those to a common denominator of 36. So it's gonna be 9 over 36 minus 5, no, how about 4 over 36 equals 5 over 36. And that's gonna be my c squared. C is gonna be plus or minus the square root of 5 over the square root of 36. The square root of 36 is just 6. So there's where my foci are gonna lie.
Don't forget the 6 under 4 over 36. It just looks like 4 over 3.
Thank you. It might help to get a decimal value for that if you're trying to plot it, somewhat reasonably. So let's do that. Let's do square root of 5 divided by 6. So about 0.37. For purposes of graphing it on an exam, about 0.4 would be wonderful. So I'm just going to put it up here and down here, F1 and F2. F1 would have coordinates at 0 and square root of 5 over 6. F2 would have coordinates at 0 and negative square root of 5 over 6. Okay. How are we looking on that one? Thumbs up? Grumble, grumble, grumble.
I have a question.
Yes.
Is the bigger one always gonna be F1?
Oh, it doesn't matter what you call F1 and F2. I just gave that some labels.
Okay, so
Yeah, I have no preference there. There is one last thing that I want to find, and that's the eccentricity. I'll cover that after I.
What is the number above 36?
This one, that's a 4. Sorry. So what I did here is I got common denominators, and the common denominator is 36. So what you can do for that first one to get a common denominator is you can multiply by 9 over 9. That gives you this. Likewise over here, if I multiply by 4 over 4, again, I'll get a denominator of 36. So changing to common denominators allowed me to subtract the numerators. Okay. Thanks, Dame. I think there was another hand up. Yes? No? Christian?
Would you be okay with us using decimals?
No, not for these.
Okay.
I do want exact values for these. So, I mean, you can check yourself on a calculator to an extent. The problem with checking yourself on a calculator is that you have to have y solved for.
Oh, okay.
So that it makes it a lot more challenging. What that would look like here is you'd have to solve for y. 4y equals 1 minus 9x squared. Then divide by 4. 1 minus 9x squared over 4. And then take the square root. Plus or minus square root of 1 minus 9x squared over 4. And then graphing it means you have to plug this and this in separately because your graphing calculator is not going to do a plus or minus for you. So the graphing calculator is not exactly set up to do these things so nicely. I did want to come back to the eccentricity here. The eccentricity. To me, it has kind of the same root as eccentric, like an eccentric millionaire, somebody who's kind of crazy. How strange are you? Your eccentricity is going to be C over A, where C is the distance to the focus from the center. Distance from focus to the center. And A is the distance from the center to the larger, or distance to the center to the vertex along the larger axis. That's a better way to say it. Distance from center to the vertex along the major axis. And I'll diagram what that looks like for you in just a second. Give you a chance to copy that down. So this distance here, that's C. And the distance to your vertex, the longer one, that's going to be your A. So it's going to be the ratio of those two distances. So C here and A here. In our particular case, easier of those two numbers was A. A is just 1/2. So let's take C, which is square root of 5 over 6 divided by 1/2. You remember the trick to divide two things that are fractions?
Flip and multiply.
Yeah, flip and multiply. So you'd be multiplying this by 2. So it's going to be square root of 5 over 6 times 2 over 1. And that 2 and this 2 will cancel, so the eccentricity is going to be square root of 5 over 3. The closer this is to 0, the more circle-like your ellipse will be. The closer that is to 1, the more stretched out and cigar shaped your ellipse is going to be. A lot of comets pass the sun in an elliptical shaped orbit. Last summer there was one called the devil tail. It's because if you looked at it just right, you'd catch kind of a green forked tail, I think, to it. So at least had a forked tail. I can't remember if it was green or not. I think it did. All right. Let's move on. Let's move down to example G, reverse engineering one of these things. So that's going to mean something like this. We've got x squared over a squared plus y squared over b squared equals 1. I want to figure out what those numbers are for this particular case. And you get a little bit of a help here. For instance, they tell you that this distance is 2. Now what is that distance in terms of all the letters that we've been using, A, B, and C?
C.
That's C. So C equals 2. And I know another distance, that's this one in this direction. But that's not C equals 2. What is that?
B.
Is that B?
That's A.
I thought A was.
A has to be underneath the x coordinate, right? And you're moving a distance 2 there. So, or A has to be under the x variable. So this is going to really be x squared over 2 squared. So x squared over 2 squared plus y squared over b squared equals 1. So I'm part of the way there. I mean, that's a good start. I mean, if you did that much, I'd at least give you a point. But I need to figure out what b is. And so, is b going to be bigger than 2 or less than 2?
Bigger.
Has to be bigger than 2, right? Because b is going to be this distance right here. And that distance has to be bigger than 2. So I'll write c squared equals b squared minus a squared, which in this case is going to be 2 squared equals b squared minus 2 squared again, which feels a little weird and strange, but it's okay. Let's put some numbers in here. B squared, 4 equals b squared minus 4. How are you going to solve for b?
Add 4 to the other side.
Add 4 to both sides. Thank you so much, both of you. 8 equals b squared. Square root of 8 is b squared. And that's it. There's your answer. So it's x squared over 2 squared plus y squared over the square root of 8 squared equals 1. If you wanted to just write it as y squared over 8, not 8 squared, but over 8, I'd be fine with that as well. There's your answer. Nice. Typically speaking, if mathematicians give you some information in a problem, you're gonna need that. And the thing that we needed, you know, in addition to A equaling 2, was that C was equal to 2. All right. Last but not least, are we okay with example G? Thumbs up on that one? Yes, all right, thank you so much. Let's look at example H. And again, we can start out with x squared over a squared plus y squared over b squared. And immediately fill in one number. Brianna, what's that one number I can fill in here? Which one? A or B?
A.
Yeah. Why A?
This is the x-axis.
Yeah, it's along the x-axis. This distance here is A. So A is equal to 15, so this is going to be 15 squared. That's where that's coming from. Over, underneath, x squared. So x squared over 15 plus y squared over b squared equals 1. And okay, great. So I got one of these, but I need b squared. What am I going to do to find b squared? I don't have any information on C, but I do have some more information.
I'm gonna say, is it 10 and 5? Wouldn't that be like the
10 and 5 is not the foci. How's,
focus or something?
yeah, foci. No, it's not. How do I know 10 and 5 is not the foci?
It's not.
Yeah, it's not on the major axis, right? So to be the focus, it would have to be on the major axis. But there is something you should probably think about in regards to 10 and 5. Does anyone know what that would be? Yeah, that's an X and that's a Y. So I can plug that into my equation, X and Y.
I was thinking of it around there.
You were getting there, you're getting there. X squared over 15 plus, darn it. 10 squared over 15. That's horrible. I'm so annoyed at myself. Let's see, will that color it over? Yeah, I guess it does. There we go. So 10 squared over 15 plus 5 squared over b squared equals 1. So see if we can't solve. That's going to be 100 over 225 plus 25 over b squared equals 1. Let's regard this as 225 over 225. Why would I do that? Why would I rewrite this as 225 over 225? Yeah, it's an LCD between these two. So if I subtract this, I'll end up with 25 over b squared equals 125 over 225. Now I could, if I wanted to, put that in lowest terms. 25 goes into each of these. That's going to be 5 over 9. Make my life a little bit easier with respect to solving there. If I have 25 over b squared equals 5 over 9, what could you do here? Zach?
You could multiply 5 to 59.
Cross multiply maybe?
Oh, cross multiple, sorry, yeah.
So 5 times b squared equals 25 times 9, which is 225. Divide both sides by b squared, or by, not by b squared, but about by 5. B squared equals 45. So what would b equal? So I'm just dividing b squared, or by, by 5 on both sides.
Square root of 5
Yeah,
plus or minus.
It's just
yeah, we'll just do the positive root. B is gonna be the square root of 45. Great. Overall, your answers should be, let's see, right like this. Your answer should be x squared over 15 squared plus y squared over square root of 45 squared equals 1. And again, if you want to just write y squared over 45 and not write the square root squared, that's fine too. But there is your final answer. Sweet. Comments or follow up on that? All right, it felt like a lot. Then we should take a break. All right, see you in 5 minutes.